Great glowing clouds are blown thousands of miles into space from the seething, turbulent surface of the sun. This same terrible energy, subdued by distance, gives life to the Earth. Our sun is a star, moving through space and carrying with it all the train of tiny objects which make up our solar system. The path which our sun takes into space is represented in this model by this straight line that you see going right straight through it. It's moving along that line at a speed of about 12 miles a second. And as the planets move with the sun, but pass in orbits about it, their paths are represented by a rather elongated spiral, which goes continually around and around the sun, following it as it moves. This motion, of course, is continuous. It doesn't stop. It keeps right on going. Now, the direction in space toward which the sun is moving is a point in the eastern edge of the constellation of Hercules. It is just about here. And here you can see the constellation of Hercules represented by the conventional gigantic figure of a giant kneeling upside down. Now, don't let that constellation figure worry you. If you were to go out on some fine clear night and look up and see a giant upside down kneeling in space, you'd better go back in and lie down again because something is wrong. This is just to identify the figure. And here is the place toward which the sun is moving. This is called the apex of the sun's way, and it was discovered by one of the astronomical greats, Sir William Herschel. He found it by observing that the stars in that direction seemed to be moving apart from each other in a motion which was independent and separate from any motions they may have had of their own, just as the trees in a forest move apart as you approach them and come to them. There have been some slight alterations to the first point which Herschel selected, but it is generally very close to this point in the eastern edge, as I said, of Hercules. There is a corresponding point on the other side of the great celestial sphere, which can be seen only from the southern part of the Earth, which is called the antepex of the sun's way, because there the stars seem to be pulling together as the sun moves away from them. Of course, this motion, too, is continuous. It never ceases. The sun keeps right on going. And in billions and billions of years, when the sun finally does arrive at this point in space, there will be new vistas opened, a new apex of the sun's way, and undoubtedly new star formations or constellations which we can see then. To us who live upon the Earth, the sun is an extremely important star. It is bright and it is hot. So bright, in fact, that none of us can look at it, even though the sun is 93 million miles away from us. And it is hot. The surface of the sun has a temperature of about 10,000 degrees Fahrenheit. Now think what that means. If it were possible, for example, for you to bring your oven up to a temperature of 10,000 degrees, this is what would happen to your stove. It would melt everything in it, every metal, become for an instant a little pool, a little puddle of glowing metal, and then vanish in a bright cloud of gas. For there isn't any element that we know of that would not instantly become a gas at a temperature of 10,000 degrees. Temperatures in the interior of the sun, however, must literally be measured in the millions of degrees. The inside of the sun has a temperature of somewhere between 30 million and 50 million degrees Fahrenheit. As we see the sun, it is most impressive. Here is a bit of the sky, and it would take 720 suns to make a complete circle of suns edge to edge going right around the sky. The diameter of the sun is 364,000 miles. It would require 345 Earths placed edge to edge to make a belt completely around the sun. And if we were to hollow out the sun, make a sort of a super bowl out of it up there and fill it up with Earths, we'd need 1,300,000 Earths to fill that bowl. The light of the sun, measured in terms of the full moon, is equal to 400,000 full moons. Now, there isn't room for that many full moons in the sky, but that's what there'd have to be if we were to equal the sun's light in that way. And if we took all the stars that we can see and put them all together into one gigantic superstar, it would take 6 million of those to equal the light of the sun. The sun is a gas. At those temperatures it has to be. It's not solid. So it is not as dense as a solid body of the same size would be. Still, there is enough material in the sun to give it a tremendous gravitational pull. It has a surface gravity which is about 28 times the surface gravity of the Earth. If a normal man weighing about 150 pounds could possibly walk around on the sun, he'd weigh 2 tons. And unless he had considerably more strength than he had on Earth, he couldn't even stand up. He couldn't support himself. It is this tremendous gravitational pull of the sun toward the center that gives the sun the very clean outline that we see when we look at the sun. And you can see it here, how sharp that edge is, even for a ball of gas. And speaking of seeing the sun, I think this is a good time for me to give you all a word of caution, which I hope you will take seriously. Never, under any circumstances, look at the sun through a telescope or any other magnifying instrument. I'm sure all of you have taken an ordinary desk magnifying glass out into the yard and focused the sun's rays through it upon a piece of paper and watched that paper burst into flame. Well, don't put your eye in the place of that paper, for a telescope is simply an elaborate magnifying glass. If you have a telescope or have a chance to use one and want to look at the sun, do it this way. Point the telescope at the sun. Then take a white card and hold it at the proper distance from the eyepiece. You can tell, just move it back and forth a little bit. And the image of the sun will be projected through the eyepiece on that card with all its details. And you can look at it and your neighbors can look at it at the same time. This is very much the most friendly way to use a telescope. The part of the sun that we can see, the great central glowing sphere of the sun, is called the photosphere, the sphere of light. And it is the part of the sun that we see in photographs of the sun, as you see it here. Now, the surface of that photosphere, barring these incidental little blotches, which we'll talk about later on, looks to be fairly evenly brilliant. Actually, it is not. The surface of the sun is really made up of innumerable tiny islands of glowing gas, little bright islands. They're very short-lived, only 3 or 4 seconds at the most. They are anywhere from 300 to 500 miles long and elongated oval in shape. They look very much like grains of rice, and in astronomy they are called rice grains. Now, here is an excellent close-up of the surface of the sun showing these rice grains, these little islands of brilliant glowing gas which make up the general surface of the sun. You can see them here, and they come and they go. They're not stable at all, and the surface of the sun is actually a seething, turbulent bed of these light islands. In between these islands and surrounding them are lanes of darkness, comparative darkness. These are actually bright. They look dark because they're not quite as bright as the islands themselves. These lanes change too as the little rice grains change and sometimes develop into dark areas which are called pores, and these pores occasionally grow into what we know as sunspots. In addition to these rice grains of brilliance on the sun, there are other more brilliant appearances which are called faculae, which is Latin for torches. Now, here are 2 pictures of these bright faculae. You can see how much brighter they are, indeed, than the general surface of the sun. And these faculae are usually associated with those dark areas which are sunspots. Now, sunspots were not known at all until the advent of telescopes. Galileo, who was the first man ever to look at the sun or indeed at anything else with a telescope, first saw these spots. And Galileo paid for his observation of the sun, for he died blind. Sunspots come in all sizes. They may be tiny, so tiny that we can't see them by any means, or they may be enormous. There have been spots known to reach an area of 250,000 square miles, similar to the one that you can see here now. They are tremendous things. And they are rather complicated, too. Here is a picture of a sunspot group. Now, sunspots are generally composed of two definite areas. There is a dark area, a central area, which is called the umbra, which means the shadow. And surrounding that dark area, there's an area which is not quite so dark, which is the penumbra, or the almost shadow. And in many sunspot groups, the penumbra forms a continuous region around several very much darker groups. Now, in another picture of a sunspot group, we have a very interesting size comparison for you. Here we can see another sunspot group with its umbra and the penumbra. And down in the very corner of this picture is a little round dot. Now, that is artificial. That is drawn there, and it is the size that the Earth would be, about 8,000 miles in diameter. Now, see how many times that Earth could be dropped into one of these sunspots without even touching the sides. These sunspots are often likened to storms on the surface of the sun, but they are not. They don't move of their own accord through the gases of the sun. They are centers of terrific turbulence, however, of tremendous magnetic strength. And they have a tornado-like whirling quality which causes them to bore holes into the bright surface of the sun. The sunspots have, however, given us some very important information about the sun. Sunspots are carried around the sun by the rotational motion of the sun itself. Now, here is a series of pictures taken at intervals of a day or two. And we can begin from the top. We can see the travel of this sunspot group from left to right as we look at it. The sunspot is not moving of itself through the sun. It is being carried across our sight by the motion of the sun. And this rotation of the sun has been divulged to us through sunspots. And it tells us that, contrary to anything which is a solid sphere, the sun does not rotate evenly. The equatorial regions of the sun rotate completely around the axis of the sun in about 25 days, the most rapid part of the sun's surface. Then, the polar regions of the sun, at its poles of rotation, take about 35 days to travel completely around the sun. Sunspots have been observed for a long time, and in about 1825, it was discovered that there was a cycle of the coming and going of spots. There are periods when there are few, if any, spots on the sun. It seems completely clean and bare. And it has been found that the length of time between these two low points of sunspot activity is, on the average, 11.5 years. Now, in between those low points, there are peak periods of activity when there are a great number of spots on the sun. But the peak periods can come at any time between the low periods. They may follow a low point very closely, or they may just precede the next low point. In October of 1957, we passed through a peak of sunspot activity such as had never been recorded before. Now, that was known to be coming, and that is the reason why the period from June 1957 to December 1958 was selected for the International Geophysical Year. The activity of the sun are a very important part of that great study of the Earth and its surroundings, and it was chosen so that we could get the benefit of this activity of the sun. Now, this boring effect of these sunspots into the sun forms apertures out of which some of the terrible energy of the sun can escape and drive ahead of it invariably a great many minute particles from the sun, drive them out millions of miles into space. And we, very often, we on the Earth, are in the path of this blast of particles from the sun driven out. And here is a diagram which shows that happening. Here is the sunspot. The energy forces these particles out until they reach our Earth with its atmosphere and its magnetic fields. These spots are guided toward the Earth by the magnetic currents of the Earth. And when these spots strike the uppermost level of the Earth's atmosphere that we call the ionosphere, they have a very definite effect upon us in our daily lives. It is this ionosphere which contains the reflecting layers by means of which we can receive radio transmissions and by which we can accomplish radio telephone conversations. Now, this impact of particles from the sun very often disturbs this ionosphere to such an extent that this reflective ability is lost, and our radio transmission is poor, and transatlantic wireless telephone conversations often go dead right in the middle of a word. By way of compensation for that, however, it is this same bombardment of the Earth by particles from the sun that give us that beautiful flickering light that we call the aurora. The particles in our atmosphere are excited by this bombardment and produce the aurora for us. Sunspots usually come in pairs. We don't know just why this is, but there is a theory, and it is still very much of a theory, that there may be a tunneling effect in sunspot pairs, that we are looking at the two ends of a shallow tunnel that goes below the surface of the sun and emerges in another spot. One strange thing about these pairs of sunspots is that as they go along, the leading sunspot of a pair, leading that is in the direction of the sun's rotation, seems to retain its identity and remain a spot, while the following sunspot is usually broken up and disintegrates. Just why that should be, we do not know, but there is a great deal that we do not know about sunspots yet. Now, the central glowing body of the sun, the photosphere, is surrounded by several layers of almost transparent material, gases of course, which might well be called the sun's atmosphere. And the effect of that atmosphere, as we see the sun, is to dull the edge of the sun. Now you can see very easily in this picture that the central part of the sun seems far brighter than the edge of it. This is called a darkening of the limb, and is the effect of the light of the sun passing through a fairly shallow layer of gas, the single layer that we see here directly over the center of the sun, or having to pass through a great many thousands of miles of this gas as it comes from the edges of the sun, very much as we look at a sunset through the layer of dense atmosphere which lies directly above the surface of the Earth. Now, this atmosphere of the sun is rather complicated and has some very interesting effects upon the sun. Here is a diagram of it, and here we can see the glowing central sphere of the sun, the photosphere. Now, if we were able to get that light from the photosphere and pass it directly through an instrument built around a prism, the effect would be that we would see a number of very bright lines parallel to each other. Above this photosphere, however, lies the first of the sun's layer of atmosphere, which is called the chromosphere. It is named that way because of its color. It is a very bright pinkish color. And the lower level of this chromosphere, which is considerably cooler than the surface of the photosphere, absorbs some of the terrible energy that comes out of the photosphere, and absorbs it to such an extent that it makes the bright lines which would be produced by the photosphere look dimmer and fainter and darker to us through a prism. The upper regions of the chromosphere are where we can see the sunspots as we see them, and which have those magnificent fountains, those geysers of glowing gas, which are called prominences. Now, these prominences cannot be seen, indeed the whole chromosphere cannot be seen on the sun except at times of a solar eclipse. But here are films of those prominences, those geysers of gas. Now, we are looking at about 400,000 miles of the edge of the sun. And you can see that those prominences are going out sometimes 50, 100,000 miles away from the sun. These pictures are time-lagged pictures. In other words, the action that takes place takes considerably longer, about 100 times longer than you actually see it. But this tremendous activity is fascinating. Here are what they call coronal prominences. They start high up above the sun, apparently, and are not seen until they appear there and seem to stream downward. These are flares. We are now looking directly down at the sun. And these are these tremendous bright focuses of that activity of the sun that I spoke about when the sun is pouring out its particles into space and bombarding the Earth. Now, above the chromosphere is the outermost level of the sun's atmosphere, the corona, that pale, beautiful halo of light that we can see, again, at times of total eclipse, and only very recently by means of special instruments. And again, we can see a film, a photograph of that solar corona here. Here it is. You can see that. That is taken at an eclipse, and you can see those glowing streamers of gas coming out from all sides of the sun around the dark bulk of the moon. Now, the corona changes shape according to the sunspot condition of the sun. At periods when there is very little sunspot activity, the corona looks very much like this. And as you can see, the polar regions of the sun have the corona very close to the surface of the sun. And these little sharp rays called spicules give the sun an appearance as though it had just had a crew cut, while the corona in the equatorial regions extends out considerably farther from the sun than it does at the poles. Now, this whole picture is shown here at an actual film of an eclipse. You can see just what is happening there. This is a corona taken at a minimum sunspot activity. And if you watch it, you can see that it seems to move, it pulsates. Actually, that is not a motion of the corona. That is a variation in the intensity of the light that you see. It's growing brighter and fainter and brighter and fainter. And frankly, some of this apparent motion of the corona is partly due to the camera and the way that light registers on camera film. But this pulsation, it does exist and is a pulsation in intensity rather than an actual motion in the corona itself. This corona gives about half as much light as the full moon at times of eclipse. Now, if we take another picture of the sun, this time during a period of tremendous sunspot activity, see what a different aspect the corona has. As a whole, it is much more evenly distributed and evenly spread out around the sun. But the distances in every case are greater. And it is possible that these gases are forced out from the surface of the sun farther by the tremendous activity going on there, which escapes in some manner from the center of the sun through these sunspots. There may be times at periods like this when these streamers, these coronal streamers, reach millions of miles into space and may extend even as far as the Earth. Of course, no possible harm can come to us then because this is very tenuous gas, very, very thin, and the Earth's atmosphere is so much more dense that it effectively bars us from any activity or whatever might result from that contact. There is a tremendous mystery hidden in the corona here, too. Measurements of the temperature in the outer regions of the corona, sometimes as far as 1,000,000 miles from the surface of the sun, a whole solar diameter away, show that the atoms there are behaving as though they were at a temperature of about 1,000,000 degrees Fahrenheit. Now remember that the surface of the sun has a temperature of about 10,000 degrees, and yet sometimes as much as 1,000,000 miles away from that surface, the temperature is 1,000,000 degrees. The smoke of the bonfire seems hotter than the fire, but we don't know why. Now, when I spoke of fire there, I didn't want to mislead you. There isn't anything burning on the sun at all. There is no consumption. In fact, if the sun were made completely of the finest coal, it would have consumed itself in 5,000 years, and where would we be? What is going on there is a series of 6 very complicated thermonuclear reactions. And the whole result of this chain of reactions is to transform 564 million tons of hydrogen into 560 million tons of helium every second of the sun's existence. Now, this means that the sun is losing 4 million tons of its mass every second. That loss, that matter, is transformed into energy. And that energy is the light and heat that we get from the sun. The sun produces 5 million trillion tons of energy every second. Now, the Earth doesn't occupy very much of space. And the proportion of that energy we get is just 1 part in 2 billion. But at that, it is 70,000 horsepower per square foot of the Earth's surface, or about 5 million horsepower per square mile. Now, that is more energy than man has been able to manufacture in all the time he has lived upon the Earth. This is our sun as a sun, the magnificent sun that gives us life and heat. And since our sun is a star, it is extremely important to us because it is the only star near enough to us for us to be able to see its surface. And remembering that the sun is a star, how does the sun compare with other stars? Frankly, it is an average star. If we were able to put our sun as far away from us as most of the bright stars are that we can see every night, we wouldn't even be able to see the sun. Now, there is a star seen from the southern part of the world, which is almost a twin of the sun, a counterpart of it. And it happens to be the sun's next-door neighbor, the nearest of all the stars to the sun. It is in the southern constellation of the Centaur, and it lies not far from the Southern Cross. Now, here is the Southern Cross, right in the center of this picture. And here you can see 2 bright stars near it. The farthest of those stars from the Southern Cross is the star Alpha Centauri, the nearest star in space to the sun, and this is what our sun would look like if it were 26 trillion miles away, for that is a star very much like our sun in every respect, size, brilliance, and so on. Here is the sun, a small, average star, but important to us. And man has had to descend a little from the high position he once occupied in the center of the universe and is guided now by an average star.
This is National Educational Television.